Hi, so in this video, I wanted to kind of take some of the ideas that we learned about in the previous chapter regarding, equilibrium constants and ice tables and things like that, and apply it to now weak acids, which we learned about also follow an equilibrium process, and just see kind of like how that application is done. So as we saw in the previous video, right, pH is kind of an important marker of just how acidic or basic a solution is. Now, when we're calculating the pH of like a strong acid or a strong base, it's relatively straightforward because we can determine the concentration of hydronium ion within that strong acid based off of the fact that it completely dissociates. Or if we have a strong base, right, we can use things like the pOH and calculate the pH through that. But with weak acids, it's a little bit trickier because the weak acids only partially dissociate. So we can't necessarily assume that our concentration of hydronium is just equal to the concentration of the acid itself, right? That's only true if the acid completely separates apart, which weak acids just don't. But we can determine the pH of a weak acid solution if we know its Ka. So consider here an example where I have a solution of hydrofluoric acid made by dissolving 1.0 moles of HF into 1.0 liters of water. Now, hydrofluoric acid itself has an acid dissociation constant of 6.8 times 10 to the minus 4. And so I want to know here the pH of the solution. In order to do this, because this does follow an equilibrium constant, I'm going to need to use an ice table. So we can picture, right, how this ice table might be set up right here. I begin with my acid dissociation equilibrium, which is again taking the acid and reacting it with water to form its conjugate base, and then some hydronium as well. Now, initially here, my concentration of the acid is 1.0 molar, right? I had 1.0 moles into 1.0 liters, and so my concentration can be written as such. Even if we're not like immediately dissolving that acid into water, whatever concentration we're given for an acid, we treat that as like the initial concentration of the acid. So 1.0 molar as our HF concentration to begin, and then 0 and 0 for both of the products here. Again, as a reminder, the water itself can be basically ignored from the equilibrium, so I just put dashes through that. Water doesn't have a concentration, and solids and liquids are always omitted from the equilibrium expression, and thus they can be left out of the ice table. I've also filled in the ice table with the change in equilibrium lines for all of my products and reactants. In this case, the change for the hydrofluoric acid itself is relatively small. I can confirm this by taking my equilibrium constant, multiplying it by 1000, and I can see that that's still less than the initial concentration of hydrofluoric acid. And so all of that is to say is that while the hydrofluoric acid loses some amount X, that amount is really, really small, and so it's still basically going to be 1.0 molar at the end of this equilibrium. The concentration of fluoride and the concentration of hydronium are both going to be X though. And so to solve for X, I'm going to use my equilibrium constant. Again, the acid dissociation constant here, Ka, has the following format. It's always going to be the concentration of the conjugate base times the concentration of hydronium, or H+, and then divided by the concentration of the acid. So again, just like the same products over reactants that we would see in other examples, this just happens to be like an acid dissociation specifically. And so I can just use algebra to solve for X here, right? Walking through the steps, I find that X is going to be equal to about 0.026 molar. And so that 0.026 molar, that is both the concentration of the fluoride at equilibrium. It's also going to be the concentration of the hydronium at equilibrium. And so if I want to find the pH of this solution, I simply take the minus log of that, and I find that it's equal to 1.58. So the process here kind of goes as follows. To find the pH of the solution, we really need to find the concentration of H+ of our solution. And we want that concentration to be at equilibrium, right? After the acid has been given time to dissociate, even just partially dissociate, right? We want to determine the equilibrium concentration of hydronium or of H+. To do that, we can set up an ice table like so and find our equilibrium amount of the H3O+. Now here I have another example, this time looking at hydrocyanic acid. And let's say that I have a solution that is 0.56 molar in hydrocyanic acid, and I measure the pH of it, and I find that that's equal to 4.73. So here I kind of want us to work backward. I want to know what the acid dissociation constant Ka is for hydrocyanic acid. So I have a few different options right here. You can kind of think how you might work backwards in this case, right, trying to solve for the Ka. You will, again, probably want an ice table of some sort just to kind of help sort things out. Also, I should mention kind of how we work with the pH equation and how we can work backwards from the pH equation. So if we are given a pH and we want to find then the concentration of H plus from that, this is basically just like an application of logarithm rules and stuff, but you can say that the concentration of H3O plus is equal to 10 to the minus pH power. So right, given a particular pH, you can determine then the concentration of hydronium in a solution. So go ahead and take a few minutes to pause, set this up, think how you might, again, kind of like work backwards through this and determine the equilibrium constant for this weak acid, hydrocyanic acid. Okay, so hopefully you've taken some time to kind of sort out all of the different pieces of information here and see how you can solve for the Ka constant itself and the value of that. Working through this example, I found that my Ka for hydrocyanic acid is something like 6.2 times 10 to the minus 10. So to walk through how I approach this, right, I first took my pH that was given and I used that to calculate the concentration of H3O+. Now this concentration that I have right here of 1.862 times 10 to the minus 5 molar, this is not my initial concentration of H3O+, right? This is the concentration after the solution has already equilibrated. That's really important to note when thinking about the pH of a solution, right? It's always going to be like after the dissociation has finished, whether that be a strong acid completely dissociating or in this case, it being a weak acid partially dissociating. But so this 1.862 times 10 to the minus 5 molar, that's basically the equilibrium concentration of H3O+, which I can plug into an ice table right here. So maybe initially I have 0.56 molar of the hydrocyanic acid. The initial concentration of both the cyanide and the hydronium would be 0, and the equilibrium concentration of H3O+ is that 1.862 times 10 to the minus 5 molar. Now keep in mind here that because we started with 0 for our initial H3O+, we end with this concentration. That means then that the change variable x is just equal to that 1.862 times 10 to the minus 5 as well. And so that x applies across the board here. Again, for this solution, x is rather small, compared to our initial concentration of HCN. And so effectively, at equilibrium, we have 0.56 molar for the hydrocyanic acid, 1.9 times 10 to the minus 5 molar for the cyanide, and then that same 1.9 times 10 to the minus 5 molar for the H3O+. I can then use these concentrations to plug back into my Ka expression, again, products over reactants. And so plugging these in, this is how I got my final answer of 6.2 times 10 to the minus 10. All right, so as we mentioned previously, a smaller Ka corresponds with a weaker acid, right, where strong acids have really, really large acid dissociation constants. Weak acids can vary a lot, right? There are some acids that are weaker than others. In this case, the equilibrium constant for hydrocyanic acid is pretty small, so this is like a very weak acid. Now, because this Ka is so small, right, we write it in scientific notation. You'll find, honestly, scientific notation is just not easy to work with. We don't really like it that much. So we will do whatever we can to try to avoid using scientific notation. So that brings us to the concept of pKa, right? So here I have the Ka that we just found as 6.2 times 10 to the minus 10. If I want to instead not write that in scientific notation, I can express this instead as a pKa value. The pKa is very similar to pH in terms of how we calculate it. It's simply taking the minus log of the acid dissociation constant. And so I could calculate this as like 9.21 as the pKa for the same acid. 9.21 is a lot easier to write out. It's a lot easier to do calculations with than the scientific notation version of Ka. And so again, pKa is just kind of another way that we represent basically the same information. It just tells us the minus log of the acid dissociation constant. What's kind of confusing, though, I'll admit, about pKa is that how it relates to Ka itself is just like a little flip. So if we have, say, a smaller Ka value, that's going to lead to then a larger pKa as a result of that. So right, they are kind of inversely related to one another. So that's to say that a weak acid, where it has a very small Ka, is going to have a large pKa. So this can be, initially just like a little confusing. You might want to think, oh, like big pKa, that must be like strong acid. That's not true, right? They are inversely related. And so if we see a larger pKa, that just means that we have a smaller acid dissociation constant and thus a weaker acid resulting. Now, one last style of problem that I want to look at regarding weak acids has to do with what we call percent dissociation. So percent dissociation is defined by the following equation. It is essentially the ratio of how much of our acid has dissociated versus how much of the acid we had initially. Now I represent this amount of acid that dissociates as the numerator right here. It's essentially the initial concentration of our acid minus the equilibrium concentration of our acid. And so if we think about like our ice table and kind of how it's set up, this numerator is essentially just the change x that we see in the ice table, right? It is that difference between initial and final concentrations for the acid specifically. So we can first start here by calculating the percent dissociation of, let's say, like a 0.40 molar hypochlorous acid solution. The acid dissociation constant for this particular acid is 2.9 times 10 to the minus 8. And so to determine the percent dissociation here, I'm going to, as usual, set up an ice table, right? So here I have an ice table for the dissociation of hypochlorous acid, or HClO. This dissociates into hypochlorite, or ClO minus, and then I've written it here just as H plus. Again, we know like H plus and H3O plus are essentially interchangeable in the aqueous phase. To save space, I didn't really want to write the plus water in the reactants, so this is kind of like our simplified form of the acid dissociation equilibria. It works exactly the same as that full form where we had two reactants and two products. It just, is a little bit neater and tighter. And again, because water never counts towards the actual K value or anything, we're not missing it necessarily from this ice table. But so I've already included here the equilibrium concentrations of our different products and reactants for this ice table. So I set things up initially with 0.40 molar of the acid and then 0 molar for both of the products. The change is, of course, subtracting from the acid and adding to the product side. And then using the equilibrium constant provided, I can solve for x and find that the change variable is about 1.1 times 10 to the minus 4 molar. And so if I want to find the percent dissociation for this example, right, I'm simply going to, again, essentially just take the X amount that I found and divide that by my initial concentration of the acid, so 0.40. I'll then make that a percentage, times it by 100%. And what I get then is a pretty small value, 0.027%. Now this really small percentage is kind of to be expected for a weaker acid like this. We have like a really small acid dissociation constant here, 10 to the minus 8 order of magnitude. So a very small percent dissociation kind of makes sense here. But what's really curious about percent dissociation is it's not necessarily like just a set value for a particular acid. It also depends on how much of the acid we start with, that is like the initial concentration. So consider here another example where I again have some hypochlorous acid, but this time I'm working with a 0.035 molar solution of the HClO. Go ahead and calculate the percent dissociation for this acid. You can pause right here, practice solving for the percent dissociation, and then we'll come back and we'll kind of compare how the percent dissociation has changed for this second solution that is with a 0.035 molar concentration. All right, so working through things right here, I'm again going to set up an ice table, again with my same equilibrium from before of HClO dissociating into its conjugate base and H+. I find through this ice table and through the equilibrium constant provided that the change X is going to be about 3.2 times 10 to the minus 5 molar. And so my percent dissociation can be calculated by taking the change, dividing it by the initial concentration of the acid, and making that into a percentage. I get 0.091%. So right, compare here, before I had a concentration of 0.4 molar and had a percent dissociation of about 0.03%. Here I have a lower concentration of my weak acid and yet a higher percent dissociation. So the percent dissociation is a little funky, right? It depends not just on the acid dissociation constant itself, but also on the concentration of the acid being used here. In kind of like a weird, hard to rationalize way, as the concentration of the weak acid decreases, we actually see a higher percentage of it dissociate. So this is just kind of like a fun effect of the percent dissociation, right? Generally, as the concentration of the acid decreases, the percent dissociation actually increases with that. Still, it remains true though that like a stronger acid is going to dissociate more than a weaker acid would. So expect a higher percent dissociation for a stronger acid. But so again, this is just like maybe a little bit counterintuitive in terms of how the solution concentration itself affects things. But so again, those are just like a few different types of problems that apply equilibrium and ice tables and a lot of the ideas from the previous chapter to now our current chapter and applications in weak acid equilibria. Please let me know if you have any questions, and I'm always happy to help. Bye.